which the country is currently, taking up. Now, in the FDP sessions that have been done over the last 3 days, we started with something on cryogenics, where we looked at as cryogenics as engineer the energy vector. Thereafter, we moved into the energy-based applications. The second day saw us going through the production to real-world applications. Thereafter, we looked at the fuel cell technology. Next, we also looked at refueling stations, very important facet, along with special types of containers. Anyone? Am I audible? I heard some voice.
Yes, sir. Yes, sir. You are audible.
Yeah, it's fine. I heard someone trying to speak. Can I go ahead?
Okay. Sir, yes, sir. Yes, sir.
So then we went on to see hydrogen energy, and we saw about we learned about the fuel cell technology. Next, we also saw the refueling stations and the special type of containers which are required for hydrogen storage. And the previous session saw the next generation energy for automobile sustainability. Now, all these topics, as I was going through the program of the FDP, they're most centered towards various applications or development of green hydrogen processes, etc., etc. However, since we have to survive in the global arena, and we have to we look for not only the Atmanirbhar program, we also look for exporting the green hydrogen and green ammonia to the rest of the world. We also look for being a significant player in the green hydrogen sector. And for that, it is very important for us to adhere to the standards, specifications, and look at the interoperability and also the regulations which exist in various parts of the world. So this is very, very essential. This particular topic is essential for adoption as well as business growth, because ultimately whatever we do in the academic institutions, the research, development, etc., it is primarily, to feed as a feedstock to the business world and look at how we can contribute to changing the life of 1.4 billion people in our country. So with that as I aim, I think this today's session, I'm sure you're going to, enjoy it. I'll not stick to the time of 1.5 hours. Maybe we are able to summarize, or maybe we are able to complete it in much shorter time, because today the intent is to give you a complete bird's eye view as to what exactly the standards, what are the regulations, and what are the clearances which are required. A bird's eye view, because if we go into the standard development of each and every aspect, this is going to take a very, very long time, and it's going to be a very, very tough task. So today's session primarily would be, giving you an overall view, and based on your requirements, maybe we can connect separately or through any other program wherein we can dive deeply into each of the aspects. Now, this is what the agenda I thought would be apt. Let's look at what is the National Green Hydrogen Mission, some important and very interesting facts about the journey of green hydrogen in India. Then we look into the standard certification and the regulatory approvals which are required for setting up the green hydrogen manufacturing units or stations within the country. We look at the standards which affect the production, storage, transport, and the end use of green hydrogen. Next, we also look at the testing infrastructure, because we may have the standards, but then ultimately those standards, whether the equipment being manufactured or whether the hydrogen being produced, is it meeting those international standards or not? For that, it is very important to have a robust testing infrastructure in the country. And therefore, we look into this particular facet briefly. And lastly, I'll give the recommendations with a very, very clear, data points, which the academia or eminent faculties like you can consider in your respective institutions or as part of your own research projects which you can give to the students to go forward. And this would not only help your academic institute, but it will also help the country in moving in a positive direction as regards the standards and overall green hydrogen sector is concerned. So with this, I just take a very, give you a brief background, historical background about the green hydrogen journey in the country. So it all started in 2003 when the National Hydrogen Energy Board was constituted. And this was constituted under the then Ministry of Non-Conventional Energy Resources. Today, the same ministry has been renamed as Ministry of New and Renewable Energy. Another interesting fact was the National Hydrogen Energy Board in 2003. The chairperson was Mr. Ratan Tata, and he was given this responsibility for driving this entire thing. After 3 years, sometime in 2006, the first National Hydrogen Energy Roadmap came up. And this brought out two important dimensions. One is two important initiatives were identified. And first one was the GIFT, that is the Green Initiative for Future Transportation, looking extensively into the transport sector. And then the Green Initiative for Power, that is addressing your power sector. However, not much progress happened between 2006 to 2016. And post Mr. Narendra Modi was elected as the Prime Minister in 2014. A review was taken in 2016 of the NHERM. And then very, very clear directions came out post that meeting. Why I am able to share this is because in a couple of meetings I was present and I had seen the first-hand experience of what transpired and how things moved thereafter 2016. Thereafter in 2020 and 21, Niti Aayog in partnership with RMI, that is RMI is a short form of your Rocky Mountain Institute. Now, Rocky Mountain Institute is is a US-based non-profit establishment which started its work in sometime in 1976. And thereafter, sometime in 1985, the company was formally, registered as RMI. And then this is a company which is or organization which extensively works into the carbon reduction or energy transition, and they come up with very, very interesting reports. So Niti Aayog had partnered with RMI, and they published their first report on green hydrogen. On 15th August 2021, Prime Minister Modi from the ramparts of the Red Fort announced the emphasis for energy independence by 2047, and that is the roadmap he gave for the Amrit Kal. A couple of more things which happened in 2021, which I have not captured here, and that was taking a cue from what the Niti Aayog report came out and what the directions of the Prime Minister were. NTPC took the lead, and NTPC came up with certain pilot projects. So we can say that in India, it was NTPC who led this entire hydrogen revolution. Of course, the thoughts came from the Prime Minister himself, thereafter with Niti Aayog and the RMI reports. Finally, I had the opportunity of working on the initial drafts of the National Green Hydrogen Mission, which was released on 4th January 2023, giving very, very clear, targets to be achieved and what are the initiatives that need to be taken. And I would be covering the same in the subsequent slide. Needless to say that the journey still continues, and it's a very, very exciting journey. Now, let's talk about the National Green Hydrogen Mission, the goals and the objectives. As I said, the mission was launched sometime in January 2023, and there was a overall, once you notify a particular mission, there has to be a budget allocation. Until and unless there is a budget allocation which happens, things actually don't move in the government. And accordingly, outlay of 19,744 crore rupees was made for the National Green Hydrogen Mission, and they were given a mandate for positioning India as a global leader in green hydrogen production, use, and exports. Now, what were the core objectives? The core objectives, firstly, was decarbonization, reduce carbon dioxide emissions by 50 million metric tons per year by 2030. Also bring in energy security. Now, I just want to share a couple of, digress a little bit. We are all aware of what's happening in the geopolitical scenario today. We have the Russia-Ukraine war going on for a very, very long time. We had also the Gaza conflict, Israel and the Gaza conflict, and all this, along with the reigning of the new Trump regime in US, has put very, very serious security and energy challenges, I would say, onto the world. And India is no, separate from that. And a couple of figures, I think that would establish what I'm trying to say is that in 2021-22, India imported about 10 lakh crores of fuel. The figure in 2022-23 rose up to 13 lakh crore rupees a year. In 2023-24, the figure came down to about 10.5 lakh crores. And in the current year, which started from April to October 25, we have already imported close to about 61,200 crore rupees of fuel from various countries. So what does it imply is that we are spending a lot of amount for a procurement of fuel for our requirements from as part of the imports. And therefore, at least if we are able to reduce 10%, if you are importing close to about 10.5 or 10 lakh crores a year, if we are able to reduce, a year-on-year imports by at least 1 lakh crore, that would contribute to our, that would help other sectors grow and reduce our dependencies on the other countries. Also, it is a force multiplier. It has got this green hydrogen mission is touted to have a multiplier effect in terms of the job creation, wherein we are looking at close to about 6 lakh jobs being created and close to about 8 lakh crores of investments coming in. Last but not least, we also wanted, or rather aspire to have the technological leadership in green hydrogen because of various reasons, which I'll talk about as we move ahead. A point to be noted here is that the technologies which are being developed in Europe or China are suited for those particular countries. In case of India, the base plateau or the base temperature, if we take an average, is close to about 30 to 35 degrees. I mean, you look at Rajasthan, you look at the high altitudes, and the electrolyzers which come from China or from Europe, they have a base plateau of about 25 degrees centigrade. Hence, in many occasions, it has been found that although those electrolyzers or those equipments are very well functioning in those respective countries, but they do not, they were found to be wanting in case they were used in India. And there has been many, many cases of such nature. So we need to develop our own technology. We need to develop our own standards and therefore be a leader in green hydrogen, sector. What are the key targets that have been given? Mainly, we need to have a green hydrogen production of minimum 5 million metric tons per year. That is the first target which has been given, and add about 125 gigawatt of associated renewable energy exclusively, being generated using the green hydrogen. What is the current status? Let's look at this. As part of the, and I'm covering up to as on May 25. When it comes to there are two parts. One is the green hydrogen production, and the second part is the green electrolyzer manufacturing or manufacturing of the equipment which would be used for producing green hydrogen. So for the green hydrogen production, there are 19 companies which have been awarded the tenders, and they are supposed to create a capacity of close to about 8,62,000 tons per annum. That is the capacity which has been given. Also, when it comes to the electrolyzer manufacturing, 15 companies have been awarded manufacturing PLI, and the total cumulative value comes to about 3,000 megawatt. And mind you, we are looking at, we have to achieve 125 gigawatts, and in the first tranche, we have given about 3,000 megawatts per annum capacity, which has to be built up. Along with this, there are certain pilot projects which are going on. for which the budgetary allocations have been made under demand 71 of the union budget. That is 455 crore rupees have been given for low carbon steel projects, 496 crores for mobility and pilot projects, 115 crore rupees for shipping pilot projects. These are essentially for making the vessels and creating small, boats which can run on green hydrogen. And this is one of the pet projects of Modi ji. And incidentally, there were trials for boats or ferries which have taken place in Varanasi, which run on green hydrogen. When we look at the mobility part of it, there are 5 pilot projects which involves 37 hydrogen vehicles and 9 refilling stations across 10 routes, including one of the projects which have been awarded in high altitudes of Leh. Then, since we are looking at developing inland waterways also in a big manner, and also there is a mandate of refueling of all the ships which dock into Indian ports with 20% of green hydrogen. There are certain pilot projects which have been awarded to the Deen Dayal Port Authority as well as Chidambaram Port. Along with this, there are green hydrogen hubs which are being established, and important to note that these green hydrogen hubs are coming along all the coastal belt of India, starting from Gujarat and going up to West Bengal, covering the entire coastal belt of India. Now, what are the initiatives which have been taken by MNRE, that is the Ministry of New and Renewable Energy, because this is the ministry which spearheads the entire mission. And they have a site program that is strategic intervention of green hydrogen technology. And under that, they are giving a lot of financial incentives for manufacturing and production. So you remember that I had stated close to about 19,000 plus crore rupees of budget allocation being done. Out of that, 17,490 crores have been allocated for these two for the incentives under the site program of MNRE. Out of this, the bifurcation is 75% is going to go for the production and 25% is going to be allocated for the electrolyzers. So clearly, this gives an intent of the government of India. We are more focused towards the production and a little less towards the electrolyzer manufacturing. Also, there are certain policy frameworks which have been, policies which have been put in place. And one of the most important thing is energy banking. And that's a very interesting concept which has been promoted by the government of India. And under that, the interstate transmission charges, the ISTC, for the renewable energy and the green hydrogen has been waived off. So what you do is, if you're producing, let's say, green hydrogen in the state of Rajasthan, and if you're transmitting it to the state of transmitting that energy to the state of Tamil Nadu, you are not going to be levied any ISTC. Rather, you can bank your entire renewable energy in Rajasthan and draw it in Tamil Nadu. So those kind of innovative schemes are existing, and the government is promoting them. Also, there is a green hydrogen certification scheme which has come up. Again, very important, because we may make the equipment and linked to this, there is another big sector of carbon credits which is associated with it. And so therefore, the green hydrogen certification scheme is a very, very innovative and forward-looking step which the government has taken. As I said, approximately 400 crore rupees of money has been allocated for green hydrogen hubs, and those hubs are under identification and development. When it comes to the research and development infrastructure support, the Strategic Hydrogen Innovation Partnership, that is SHIP, program exists which supports the R&D. Also, there are various skill development programs which are being undertaken under the National Skill Development Center. Also, a large number of international cooperations or the MOUs are being signed with various foreign entities to harmonize the standards and facilitate the exports. Now, let's dive into the main topic of today, and which is the standard certifications, regulatory and approval. Now, first, let's look at what exactly is, how do we define green hydrogen? Because that's very important. Any hydrogen cannot be, called as a green hydrogen. So the Ministry of New and Renewable Energy notified the definition And in that, they very clearly clarified that green hydrogen is the one which is produced using renewable energy sources such as solar, wind, hydro, biomass, or other non-biogenic resources. That was the first condition. And the second twin condition is the emission threshold should be less than 2 kilograms CO2 equivalent per kilogram of hydrogen in case of non-biogenic. This is for when we are using when we are looking at the green hydrogen production. And this is measured over the last 12 months within the defined boundaries of the system. And if you want, there is a beautiful document which has been notified by MNRE, which is easily available on the net. And you can go through the nuances of the green hydrogen certification in that. Now, let's look at who are the green hydrogen certification authorities and what are the governance boundaries which have been listed for them. So authorities, the first thing is the MNRE, which is the nodal ministry, and it is the one which supervises this entire scheme. Then we have the implementation agency or the scheme implementation agency. In many places, you will see the word SIA, that is the scheme implementation agency. In case of India or under MNRE, there is a body which is called as the NICE, National Institute of Solar Energy, which is the scheme implementing agency. And that is the one which is implementing this entire thing. Then they have a technical committee which is chaired by the mission director of National Green Hydrogen Mission, and which approves all the certificates. And herein a very important facet comes in, and that is Bureau of Energy Efficiency. In many places, you will find that Bureau of Energy Efficiency has been given this responsibility for accrediting carbon verifiers. It is going to independently verify the green hydrogen mission. So it is going to act as a gatekeeper, wherein it allows only those who are going to satisfy those twin conditions, which I had mentioned in the previous slide, and allow them to do the business. Otherwise, any entity which is not satisfying those twin conditions is not going to be awarded the certification, green hydrogen certification. Now let's look at the stakeholders. The producers definitely are the important stakeholders. They are responsible for monitoring because they have been given self-monitoring provisions. They are also allowed to, they are supposed to file various reports, verifications, and they are supposed to adhere to various regulations which the government comes out with from time to time. Then we have the accredited carbon verifiers. They conduct the site verifications under the guidance of BEE and issue certification statements, right? And lastly, the MNRE or the implementing agencies, this is the one which issues, reviews, revokes certifications as per the requirement. Let's look at the standards and certifications now. We have seen till now what exactly constitutes green hydrogen, what are the agencies which are involved, and then what are the various boundaries. Now let's look at the standards and certifications. Now, why the standards are important? Because they ensure safety, reliability, and interoperability. It supports global trade and certifications because today, let's say if I'm manufacturing electrolyzers in the state of Orissa or Gujarat, and I want to import them to, let's say, Denmark or Germany, I should be able to support those global certifications. Then reduce investors' risk and accelerate development. Because let's say if I am investing a sum of about 100 crores in setting up a plant, and then that plant manufactures electrolyzers, which are going to be used only for local consumption, so it doesn't give me ROI. So if I adhere to the standards and the specifications and the various international laws, it reduces the investors' risk and therefore promotes a very good sentiment amongst the investors. Also, it enables harmonization with the global markets, needless to say. When it comes to India, let's look at the 5 entities which are currently preparing or administering the standards in India. So these are the 5 entities, that is the BIS, Bureau of Indian Standards. Then we look at the Petroleum and Explosive Safety Organization, PESO, the PNGRB. Then we have the OISD and the MORTH, that is the Ministry of Road Transport and Highways. When we look at the international organizations, there are total 21 international standard organizations, and predominantly you can see based in US, and rest of them are in Europe. Britain has one, Switzerland has two, Brussels have two, China has one, and Canada has one standardizing organizations. Now, a brief about Indian entities. Let's talk about and understand as to what they're doing. The BIS, it is the national standard body, as you are all aware, and it was established under the BIS Act of 2016. It is responsible for the harmonious development of standards, marking, very important, and quality certification of goods. Next, we have the Oil Industry Safety Directorate, which is a technical directorate under the Ministry of Petroleum and Natural Gas. This formulates, coordinates, various and implements. It's got three roles. It is not only responsible for formulation, coordination, and implementation of self-regulatory measures towards enhancing the safety of oil and gas industry in India. Very important, right? Next, we have the PESO, that is the Petroleum and Explosive Safety Organization. This is the nodal agency for regulating the safety of hazardous substance such as explosives, compressed gases, and petroleum products. Because hydrogen, if you see, compressed hydrogen is the one which is having its application everywhere, and therefore involvement of PESO becomes quite intense in the entire green hydrogen value chain. Next, we have the Petroleum and Natural Gas Regulatory Board. This organization exists to protect the interest of the consumers, right? And this entity, this is involved into various petroleum products, natural gas, and the overall aim of this organization is to promote a competitive market. Last, we have the Ministry of Road Transport and Highways, which is responsible for formulating and administering the standards related to the mobility, because that's very important today. We in the lecture which we had yesterday, we had seen about, we have talked, the speaker had spoken about the automobile sustainability. So it is MORTH not only regulates or formulates the standards for the vehicles which are going to use the green hydrogen, but also how the transportation is going to happen from one point to another point. That's again a very important facet. So MORTH looks into those aspects. We have MOUs with the following 7 organizations. First is the ISO, which is Geneva based. Then we have the American Petroleum Institute, the API. And API is incidentally independently also forayed into green hydrogen as API Green. So that is again organization which we have our MOU with. Then we have the International Electro Technical Commission. Now this is important. You will see this term in a large number of tenders which are floated by the Government of India as well as the PSUs. So adherence to IEC standards is again mandatory in a large number of standards that are being followed in India. We have the American Society of Mechanical Engineers, that is the ASME. This is primarily looking into your pipelines and the pressure vehicles. Then we have the American National Standards Institute located in Washington, USA. Then thereafter, we have the European Committee for Standardization, that is a SEN certification, which is in Belgium. And last but not the least, we have the IEEE, which is New Jersey, US, which looks into a large number of other facets, which includes your, the control systems, the sensors, etc., etc. So net, this is what it is. And when we look at the various, some of the standards which I have quoted is that is the ISO TC 197, which looks into the hydrogen technology. IC is primarily looking, that is what I spoke about. The International Electro Technical Commission looks into the fuel cells and electrical safety. We have the SEN, which looks into the European hydrogen safety norms. The Society of Automobile Engineers, SAE, looks into the fueling protocols. The API and the ASME looks into the pipelines and the pressure vessels. So this is net what is I've spoken about what the organizations which are looking into India. Then I've spoken about the total number of organizations internationally, and US predominates that. And this is a snapshot of the organizations with which India has a MOU. Now let's look at the roles and regulatory duties and public standardization bodies. BIS leads the pack with almost 62 green hydrogen standards, followed by the OISD, which has got 13 green hydrogen standards. PESO looks into 5 green hydrogen standards, MORTH 5, and the PNGRB looks into the 2 standards. So this is in a nutshell about 87 standards which India has adopted, and this is the breakdown. So now you know that which are the touch points for various standardization for green hydrogen in the country. Now let's look at as someone who's trying to establish the green hydrogen production as well as the green hydrogen equipment manufacturing in the country. There are total number of approvals which are required is about 73, which is quite huge. Out of this, the state governments have to give about 43 approvals. The central government gives about 23 approvals, and the local bodies have to give 7 approvals. If I break down these approvals into what are the broad domains, the general and legal approvals are about 27. Renewable energy is 14. Fire and safety, very important. There are 13 approvals required. Pollution control 8. Labor 8. Land allocation and use, there are 3 approvals. So net in total, this is how the breakdown is as regards the approvals is concerned. I've captured the same in a view file for easy assimilation, wherein the same have been listed in the general legal, renewable energy, fire safety, pollution control, labor, and land acquisition. So if you look at this graph per se, the state governments are the ones which have been given the responsibility of providing the maximum number of approvals, and therefore it is in the interest of those respective state governments to look at these approvals in a proactive manner if they want or if they wish to adopt green hydrogen in the respective states. And if based on the experience that I have got, there are 2 important states which come to my mind. One is the Gujarat and second is Orissa, followed by Tamil Nadu, which are leading the pack as regards the speed at which the approvals are given. So there is a lot which has to be done. The state governments, almost about 7 to 8 of them have come out with the respective state government green hydrogen policies. There are others who are supposed to catch up, and I'm sure going forward, those state governments who are yet to notify the policies will take a cue from the ones which are already have notified such policies. Now, if we look at the approvals have to be given in 2 stages. One is the pre-establishment stage and one is the pre-operation stage, right? The central government, when we look at it, there are about 6 general and legal approvals which have to be taken in the pre-establishment stage. One relates to renewable energy and one relates to the pollution control. Rest as regards the other fire safety is concerned, labor is concerned, or the land allocation is concerned is primarily looked after by the state governments. And in case of pre-operations, the major emphasis for the central government approvals goes into the fire safety, right? So this is the pre-approval and the pre-operation, the number of approvals which have to be taken, right? Now let's look at how the state governments stack up. This is on the view file. You can see the pre-establishment, the number of approvals which are required, like the general and legal are about 5, renewable energy 5, pollution control is 2, labor is 1, and land allocations are 2. And pre-operations, this moves up to, general and legal, again, 5 additional ones, renewable energy 7, fire safety 6, pollution control 3, labor is 7, and no for land allocation. That's already taken part as part of the pre-establishment. Now let's break down this entire standardization and certification further. into the broad baskets. Now this alkaline electrolyzer, I've intentionally put this image here. You see I hope you guys are able to see my cursor. The one on which I'm moving my cursor is called as a stack or the electrolyzer, right? This is an alkaline electrolyzer. So this is a stack. And the one which you see at the rear or behind this is the balance of plant. You see a large number of cylinders. You see a large number of control systems which are there, a large number of pipelines, and equally, almost about 300 to 400 valves are required, right? So this is a very, very complex, piece of equipment. And believe you me, each cylinder, each pipe, each valve, each control system, there are standards, and each standard has got a large number of tests, minimum about 10 to 15 to 20, and many a times going up to 25 tests that have to be qualified to meet those standards, right? So it looks very simple in this, it looks very neat in this, but if the moment you start looking at standards and certification for each and every equipment, each and every piece which is connected into this entire setup, it's a huge Herculean task. So if you look at the categories of the standards, it is broadly divided into the production. There are 8 standards which relate to the production of green hydrogen. When it comes to storage and transportation, there are 102 standards. End use applications, there are 52 standards. And for general safety, there are 39 standards. So these are the 4 baskets in which the standards can be divided. Globally, there are about 201 green hydrogen standards which exist. Out of that, we have adopted 87. India has already adopted 87 standards. Now, each standard requires multiple types of conformity tests because that's what I said. Until and unless you meet those conformity tests, certification cannot happen. And for the 87 existing standards in India, we just have about 6 testing facilities which can just test about 6 standards today. We have 87. We are able to test only 6 standards in India today. And that's a major bottleneck because we have to take permissions, we have to send the equipments abroad, we have to get the experts from abroad to certify these particular standards. So this is a huge area, this is a huge void which exists in case of development of green hydrogen in India. And there are testing infrastructure for 15 more standards is under development, but still this is a very long way to go. And imagine if India adopts those 201 standards, where would we be? Therefore, we need to move at a rapid pace for developing the testing infrastructure in the country. Academia as well as the private industry has a huge role to play here, and they can gainfully utilize this void and create value propositions for the organization. I mean, what stops a particular institute to create facilities of hydrogen testing of a particular, let's say 3-4 standards that not only would give you a edge over the other institutes, it will also create an additional revenue streams for that respective institute. So as faculties, I think it would be important if you can look into this particular facet. Now, status of green hydrogen standards in India. We have already adopted, like I've said, we have already adopted 87 of them. And this has been broken down into various things like production. We have adopted 3. In case of storage and transport, there are 37 standards which we have adopted, general safety 14. And in case of end use applications, we have adopted 33 standards. The standards under development, when we look at it, there are 36 standards for storage and transport, none for the production. For green hydrogen safety, it is 16. And for end use applications, there are 7 which are under development. The ones which are being considered for adoption, production is 3. End use applications are going to be 11. Then we have the storage and transport 29. And general safety 9 standards, right? And the under development standards, that is the 59 standards, right? This is the one which I'm talking about. Out of that, the bifurcation amongst those standardization agencies in India, OISD is doing work on 27 standards. PESO is working on 16, BIS on 15, and MORTH is working on one standard. Right? Now let's dive into each of them, the production standard. Now, components and subcomponents of the green hydrogen standards, let's look at them. When we look at the production standards, we broadly bifurcate it into two parts. That is the hydrogen generators and the balance of plant. When we look at the hydrogen generators, we are talking about the water electrolyzers. And in the water electrolyzers, there are a large number of tests. I mean, there is what should be the quality of water, what should be the quality of the DM water plant. So those standards and specifications come into play. Then we look at the pyrolysis. Again, very important thing, because we are looking at thermal energy for biomass, using thermal energy for creating green hydrogen from biomass, etc. Next, we also look at the balance of plant. Balance of plant has got a large number of things, like I was mentioning. It has got purifiers, it has got dryers, it has got storage, cylinders, it has got compressors, valves, etc. So if you look at the balance of plant, there are standards which are related to the carbon monoxide analyzers. There are power systems, the PSA, the pumps, and the water electrolyzers subsystems. Currently, when we look at the standards, mostly these are the ones which have been adopted by BIS. For hydrogen generators, one of the standards is IS 16509. Balance of plant is IS 1070. Balance of plant, again, for the pumps, it is IS 5639. And for the pyrolysis and the CO analyzers in SOEC, that is solid oxide electrolyzer cells. This is again a type of the electrolyzers. There are no standards which are existing. And this is globally, right, for the pyrolysis as well as for the SOECs. There are no standards existing, and therefore, if academia can take lead in this and develop these kind of standards, go through this entire thing, I think that would be a great proposition, because that would give you not only a visibility in India, but it will also give you a global visibility. Now, as regards the proposed for adoption standards are concerned, again, hydrogen generators, that is the VDI 4634, BOP, that is IEEE 1547, mostly being adopted by BIS, looks into the control systems, etc. Then we have the ISO/TS 19883 2017, again being worked up by BIS, pyrolysis, and the CO analyzers for SOECs. So we need to look into these particular facets and start working in this direction. When we look at the components and subcomponents of the for the transportation and storage, and mind you, this is the one which is having the largest number of standards. 102 standards are being used in for transportation and storage. Now, broadly, this is divided. I mean, how do you transport and store green hydrogen? You can do a gas transport or a liquid transport. You can have a gas storage, or you can have a liquid storage. And when it comes to storage, we can also use the carrier molecules. When I say carrier molecules, I'm essentially hinting towards ammonia, that is the green ammonia, which can be used for the green hydrogen can be converted into green ammonia and then transported, because there are well established standards and certification existing for such transportation in the country, because it's been going on for a very long time. Next, when we look at the gaseous transport, these are the broad buckets in which the standards are divided, dealing with the gas infrastructure, metering part of it, piping and pipeline, reverse metal hydrides, and the vehicular tanks. Gaseous storage is looking into gas cylinders and tanks, portable containers, stationary containers, and underground storage. Liquid transport, we have the first lecture which was there as part of the FDP, we spoke about the cryogenic vessels. Now those standards are getting defined here. We also look at the fuel tanks and the shipping vessels, because India is aiming for a large capturing a large portion of green ammonia value chain. And if that has to happen, India needs to export a large number of green hydrogen using our shipping vessels. So there are standards for this. Then we look at the liquid storage, that is the cryogenic vessels, bulk liquid, and the cryogenic storage again is being looked into. And out of the total standards which are there in globally, we have already adopted 37. There are 36 under development and 29 being considered for adoption. Now, I just give you a brief of what are the kind of transportation approvals which are required when you're transporting green hydrogen within the country or when you're moving it outside. Within the country, there are three important agencies. That is the PASO, the State Transport Department, and the OSD, which are supposed to give you the certificate or the clearances for transporting green hydrogen within the country. This this is the approvals are primarily in terms of route clearance, because hydrogen, as you're all aware, is a highly flammable molecule. Also, it requires a vehicle certification and adherence to the hazardous goods rules, which have to be adhered to. So these are the approvals which needs to be taken up. Now I've just captured, because you see 102 standards, and if we look at the ones which we have adopted 37, if I start talking about each one of them, it's going to make very little sense, since we are it's just a precursor and we are trying to look at the broad picture. I've just stated a couple of standards. When we look at the cylinder and the composite tanks standards, these are the ones which have to be adhered to. Pipelines and piping standards are these three, and the cryogenic storage standards are again listed. So I mean, there is a plethora of standards which needs to be adhered to, and we need to understand the magnitude of this entire thing which we are discussing. Now look at the end use applications. There are total 52 standards which are existing globally. We have already adopted 33 of them. 7 are under development, 11 are being considered, and there is no global standard. There are three things for which global standard was not existing. One was related to the pyrolysis. The second one I spoke about was the SOEC, and the third one is related to the iron and steel shaft furnaces. So these are the three standards for which there are no global standards existing. However, when we look at the end use applications, they can be divided into these 7 categories. One is related to the aviation, the land vehicles, the marine vehicles, the refueling stations, fuel cells, hydrogen fuel quality, and the distributed applications, right? And within each one of them, you can, let's say, if you look at the aviation, it is talking about the aviation turbine fuel, aviation safety. Land vehicles, we are looking at compressed gaseous fuel cell electric vehicles, then energy consumption measurements, fuel system components, hydrogen based railways, for which there are a lot of trials being done in country on the engines being run on green hydrogen. So there are standards which are existing to this. Also related to the vehicle safety. Marine, we are looking at the bulk liquid, refueling stations, fuel cells. Again, you have got standards which are for the micro fuel cells, the portable fuel cells, and the stationary fuel cells, right? So this is, in a nutshell, gives you a glimpse of what's in store when we look at the standards for end use applications. This is again, I've tried to, dive into a couple of them. The stationary power, industrial heating, refueling stations, mobility. Now, when we look at the hydrogen fuel quality standard, that is IS 16061, it defines, how the purity has to be measured. That is 99.97%. And today we are talking about 999. That is 99.999 is what most of the government tenders or the PSU tenders talk about. So those standards are coming from IS 16061. Also, it talks about the critical fuel for cell longevity, because this is one important thing. Any kind of impurity in hydrogen may make your entire electrolyzer dysfunctional. So these are the standards. We are also looking at vehicle safety standards. That is the AIS series. AIS series is the one which are notified by the Ministry of Road Transport and Highways, right? Also, then we look at the fuel standards: IS 19036, IEC 6222282, This is again a European standard. When we come to the refueling station standards, that is the IS 18538 series, part 1, 2, 3, 1, 3, 5, and 8. Again, the one important place where you can find all the repository of these standards is the BIS website. You can go to the BIS website and at least sift through various standards which exist. And as an institute, you can even take a subscription for the BIS. It's highly subsidized for the academic institutes, and you can look into these standards individually. Now, let's look at the hydrogen safety, which is the last bucket in which the standards are divided. Total 39 standards. First is the electrical installations, in which the BIS looks into the 11 standards, OIS 1, PESO 1. Fire safety and explosive safety, in which BIS looks at 3 and PESO 5. Process safety, BIS 4, PESO 7, OISD 6. And material safety, BIS 4 and OISD 1. And these are the standards, which are there, which exist as regards the hydrogen safety is concerned. I'm sure, by now, looking at these standards and the enormity of this entire gamut, I'm sure it requires a very, very deep, engagement, and I would not go into very specifics now. Let's move into the next. This is how I've captured the general safety codes which are there. Which are, you can definitely in your time go through it. Now let's look at the testing infrastructure, because we have a paucity of time, and I want to give some 5-6 minutes for that for Q&A also. And it's important to now look at how does the testing infrastructure exist in the country. And as I've already stated, out of the 87 standards, we can have testing infrastructure only for the 6 standards in the country. And this is, so as I mentioned that for the electrolyzers, and this view, this particular thing I've taken from the CEEW report, which is there in the public domain. And let's look at the electrolyzer only, the factors which need to be considered for electrolyzer performance. So why I've put this slide is it serves 2 purposes. First is it gives you a glimpse of what are the areas where you can work for making more efficient electrolyzers and the domains which can be considered for research, and also gives you a brief overview of various standards that may be affecting each part of the electrolyzers. So when we look at the performance, we are looking at specific energy consumption, which is very important factor. Today, most of the electrolyzers which are existing for a 1 megawatt, the energy efficiency is not going beyond 60 to 70%. So there is a huge scope for improving this. The efficiency of the stack as such, the BOP and the how it functions. And important thing is about the degradation rates, because today the overall life of electrolyzers is kept at about 60,000 hours of continuous working. Now, how can we make this 60,000, enhance this particular life? Because post 60,000 hours, the entire membrane, it has to go for a complete overhaul, which is a very, very costly affair. So how can we transform this entire thing, and this opportunity can be, explored? We also look at electrode life, because today electrodes, there is a research which is required for electrodes, both in terms of the material which is being used, and also the thickness of the electrodes, the efficiency of the electrodes. Look at the membrane and the diaphragms, because if you want to make the electrolyzers really efficient, energy efficient, we need to have a zero gap, tending towards a zero gap between the electrodes. So we need to have those efficient membranes that can withstand pressure of more than about, let's say, 80 bar or 100 bar, which exist within the stack. yet deliver a high efficient thing. Can we also look at enhancing the replacement interval of the membranes? How do we adapt to the variable renewable energy? Because you see, when we're talking about green hydrogen, the electricity has to be generated using the solar or the wind or any other renewable energy mode, which is non-uniform and may change by the day, the season, or the hour. So how do we make our electrolyzers more adaptable to this? How can today the alkaline electrolyzers, and if you look at the alkaline and the PEM electrolyzers have a lesser startup time as compared to the AEM. So can we look at making this startup time less post the shutdown? Because at times it is important for having a shutdown due to any catastrophic failure. So how do we do that? How do we improve the overall characteristics, that is the operating pressure and pressure drop? Because output pressure, let's say most of the electrolyzers in the market today are generating hydrogen at 10 bar. But then if we are able to generate the same at, let's say, 30 bar or 60 bar pressure, that would reduce the number of compressors which would be required for the end usage. So how can we do that? Can we there is a since there is a huge amount of electricity heat which is generated by the stack, that is the equipment. So can we use this heat recovery to generate green hydrogen again? Can we bring down the operating temperature? Can we optimize it? So these are some of the areas that can be looked at. And last but not the least, how do we increase the hydrogen purity in a more efficient manner? Because today the asking is about 99.999 in most of the government requirements or the PSC requirements or the requirements abroad. So how can we improve the purity of hydrogen? Those are some of the areas that need to be looked into. Now, some of the standards, and the associated tests, like I was saying that there are, to say that it is just a simple standard, that is IS 14885, right? But look at the number of tests which have to be conducted and adhered to get this kind of a certification. And what is this certification all about? It is a polythene pipe for supply of gaseous fuels. For that, these are the specifications. Now, these are the tests to be conducted. A has got 7, B has got 7, each subhead. And these are the accredited labs which are conducting these tests today, right? Similarly, there are standards for which there are no accredited labs as on date, right? So this is the enormity. This is same standard continuing under the subhead C, that is a test for pipes. There are 15 tests which have to be conducted. So net, if you look at it, there's 7 plus 7 and 14, and this is 15. There are 29 tests which have to be conducted for just IS 14885 in case the equipment has to be certified. So imagine if you consider the entire balance of plant, entire electrolyzer, you consider the fuel stations, refueling tanks, etc., etc. The number of standards and the number of tests that have to be adhered to. So this is primarily meant to bring forth the enormity of the entire thing. Now, as regards the testing infrastructure, this is a brief overview. Only 6 standards can be tested in the Indian labs. And when we look at the standards, now this is important. You look at the standards with identified tests. With identified tests, BIS has got 53, and there are 50 standards for which we do not have the identified test today. When we look at the BIS and PESO standards, there are 3 standards for which we have identified tests, and there are 11 for which there are no identified tests. Look at MORTH, which has 6, OISD has 40, and PESO has 35. PNGRB has got 2 tests for which the standards, the tests are yet to be defined, like these which have been listed, A, B, and C, which have been mentioned. Such tests have not been identified for the ones which have been shown in the violet lines. So there is a huge gap which exists, and we need to have the national hydrogen test centers in place. And testing requirements related to green hydrogen are yet to be fully identified in India. So herein again, there is a huge scope for academia to step in, work in tandem with these organizations, identify if you can help them identify the test, work with them for towards creating those tests. I think that would be a great scope to work ahead. Now, this is, again, a little busy slide, but then gives out uh, information about those testing infrastructure in the country. We have a CSIR, National Physical Lab, which is located at New Delhi. It is already existing, and it gives works in the domain of hydrogen gas metrology, gas purity analysis. It gives a references, gas mixtures, calibration of hydrogen analyzers, etc., etc. Right, and it also supports ISO 14687. Next is the National Institute of Solar Energy. There is the scheme implementation agency. It has got an important role, located in Gurgaon, and it looks since it was initially created for solar proliferation of solar in the country. They specialize into the photovoltaic or the renewable testing. Now they have forayed into training of green hydrogen, and it is a scheme implementation agency. So all tests related to the PV, etc., are being done at the NIAC. Then we have the Central Power Research Institute, CPRI, and which looks into the fuel cell and the hydrogen research, testing, located in Bangalore, and primarily focused towards the fuel cell testing, as I said. This is where it works. Then we have the IIT Madras, which has taken a pole position when it comes to the electrolyzers in the country is concerned. So they have got established an innovation hub in partnership with Hyundai, and they are carrying out major R&D projects and pilot test centers at IIT Chennai. They have established, let's say, a pilot scale electrolyzer testing facility at IIT. Fuel cell test standards, pilot demonstrations are there, component validations are taking place, and so net, it is a major facility for electrolyzer and fuel cell testing and demonstration. Then we have IIT Bombay, which is again working in the fuel cell and storage domain, which it has got small, medium scale fuel cell stations. For the PEM, that is PEM electrolyzers, works in hydrogen storage material testing, very important, that is the metal hydrides. So this is where IIT Bombay is. And then we have IIT Delhi, along with other IITs like IIT Roorkee, Kanpur, Madras, working together, looking into, again, electrolyzer cell design, catalyst membrane, again, very, very important. Because today the membranes are being imported from Belgium, that is the Zephyron membranes. India needs to have its own technology, its own membranes in-house, because that is something which will cut down the cost of electrolyzers to a large extent. Today, the 1 megawatt of electrolyzer costs about 4.5 crores, out of which the import is close to about 70 to 80% today. And if we have these membranes, the electrodes being manufactured within the country, you can imagine what kind of a transformation it can result. Then we have the other national labs, and the PSUs also have stepped in, like the BHEL, NTPC, which are again looking into the material hydrogen embrittlement. Now, the important point to be noted here is everyone is today talking about embrittlement, because there is a thought, there is a pilot project which is undergoing currently in Baroda, wherein they are looking at green hydrogen blending with the pipe natural gas, almost 5 to 10%, and how it can be used in the city gas distribution. And they found that the moment the hydrogen concentration in this concoction goes up, it leads to the embrittlement of the pipes and cracking of the pipes. So there is a research which is required for looking into the materials which can be used for making the green pipes for city gas distribution. And this is again a very big area where people can work and make a real difference. Then there are MNRE funded dedicated green hydrogen test centers which have come up, which have been planned, rather not come up, which have been planned. And around 200 crore rupees have been earmarked for them. There are two rounds for call for proposals which have taken place. In the first round, there were 5 proposals which have received, and the second round, there are about another 7 to 8 which have been received and under evaluation under MNRE. Now, to summarize it, gaps in testing capabilities. We have only about 6 standards which can be tested in the accredited labs. And today we can test only up to 700 bars. We need to go up. There is no liquid hydrogen handling test facilities. We have limited fuel cell qualification facilities. No salt cavern storage testings. There is a major gaps in electrolyzer testing. We need to have national hydrogen test centers. Testing requirements related to green hydrogen are yet to be finally identified. You must, if you remember the slides, we are yet to identify the number of tests which have to be taken up for each of the standards, right? And 200 crores have been allocated under demand number 71 of the union budget for setting up of these laboratories. A point at the end of it, it is the collaboration and focused effort which is required between the government, industry, and academia if we want to, want to be real leaders in the green hydrogen in the world. Now, I come to the last portion of my presentation, and the industry, certainly is the one which is facing these challenges. We have a large number of approvals, and they are that too fragmented, as we have seen, 73 approvals to be taken, state as well as central government, then pre-establishment, post-operation, right? We have limited testing labs. The current cost of compliances is very high. There is a huge gap in the talent and the skill. I mean, today we don't have people where the number of people who are industry ready for working in green hydrogen sector is very less. And last but not the least, we have lack of harmonized certification in the country. So these are the challenges which the industry is facing, and this is where industry academia collaboration can help. I would sincerely recommend that if renewable energy technologies can be included in the curriculum, respective curriculum of both the undergraduate and the postgraduate courses, you can give small green hydrogen projects to the students to test the financial viability, and then thereafter having these test cases, test pilot projects being demonstrated to the industry for better engagement and investments. Then establish facilities to standardize performance metrics and validate electrolyzer efficiency under real world conditions. Remember, I had spoken about the various facets. How do we increase the life of the electrolyzer, the membrane quality, etc. Those can be looked into. We need to strengthen the transition from laboratory scale research, that is going from the tech readiness level 3, which is the basic one, to the tech readiness level 7, where the industry is ready to adopt it. So the transition has to be very important and time-based, and due focus needs to be given in that, because ultimately what happens, what I've seen is, even as since I've been in IIT, I've seen what happens is the academia is more interested in research papers and filing of the patents and the PhDs, right? Instead of that, if we look at the real implementations, how the research can be commercialized, that is going to make a huge impact. Then focus on identifying critical industry challenges and designing targeted solutions, right? If you come up as a solution provider, I'm sure more than the industry would be more than happy to welcome you, and because you're going to give market ready outputs. Promote collaboration across disciplines. You see, when we look at electrolyzers, it involves the interdisciplinary. It's a interdisciplinary domain wherein you have the mechanical engineering, the chemical engineering, electrical, and the electronics, even the computer science. All pitching in to create this entire subsystem. So you can create those kind of interdisciplinary programs and facilities in your institutes. And then establish structured arrangement between the industry and academia and policymakers, to align research priorities and commercialization strategies, because you need to be very clear that what industry wants. Let's say if you're engaging with important players like the Reliance or the Adani, etc., and there is a kind of a synergy of what they want and how you can contribute into that, that's going to be a great game changer. And shift academic performance parameters to prioritize real world impact. That's what I mentioned. Rather than looking at patents and PhDs, look at to you need to prioritize into real world impact, how it is going to make. Also look at industry collaboration and technology transfers. Now, suggested areas of research which can be taken up. We have discussed some of them. You can work into the hydrogen safety domain, wherein you quantify explosion limits, then the dispersion behavior, material compatibility to establish safety benchmarks. You can look at the hydrogen purification, that is focus on improving the methods for purifying hydrogen for various applications. You can also look at the storage innovations, explore advanced alloys, because you see today, when we look at the PEM electrolyzers, there are a large number of noble metals being used, and those noble metals come from China. So how do we reduce our dependencies on those noble metals, come out with certain advanced alloys, composite materials, and alternative storage methods to overcome those bottlenecks? When we look at the hydrogen combustion as such, right? When we look at the furnaces, etc. Now this is important. Like how do you challenge the flame speeds? Then the ignition energy, how can you generate more energy? The material compatibility for safe and efficient combustion systems. How can you design efficient burners, right? How can you change the burner geometries and the materials which are being used when you use the fuels like hydrogen and green ammonia? You need to have you need to have a multidisciplinary approach wherein you combine the material science, chemical engineering, computational physics, and techno-economic analysis to drive innovation, right? So this is how I think it can be considered in your respective institutes. Some of the additional areas, research areas, which I think can be considered is how do you enhance the electrolysis technology? That is, today, potassium hydroxide is being used extensively in alkaline electrolyzers. So can you use any other electrolyzers and improve the catalyst and efficiency? Stability using noble metals, non-noble metals, that is reducing our dependence on China. Optimize membrane conductivity, minimize degradation mechanisms, advance electrocatalysts, right? Improve hydrogen storage and transports, right? Look at developing solid state hydrogen carriers, metal hydrides, and novel storage solutions. Research into hydrogen purification, compression, and liquefaction of technologies. Investigate hydrogen's interaction with materials, right? Like I was talking about the city gas distribution to enhance durability and minimize losses in pipelines, storage tanks, and fuel cells. Also look at addressing hydrogen safety and combustion dynamics, which we spoke about. Also, it's important to develop India-specific standards, because today, if I get an electrolyzer from China, or let's say if I'm getting it from Denmark or any other European country, they are adhering to those standards which are existing in those countries. And mind you, when I get those electrolyzers, import them and put them in Indian conditions, 60% of them fail the mark. And the cost of reviving electrolyzer is huge, because I can share one example. There was one electrolyzer which was imported from China. It was a 100 kilowatt electrolyzer installed in India. It worked for about a month or two. Thereafter, it stopped working because there was a huge, the membrane had given up, and due to the plateau temperature being high, the electrolyzer efficiency had gone down drastically. And when contacted with the Chinese counterparts, the cost of getting those Chinese counterparts and getting the electrolyzer repaired was 2 times at which the electrolyzer was imported in India, right? So we need to have India specific standards so that we can create we can make electrolyzers which are or the fueling stations, etc., which can work efficiently in our conditions, Indian conditions, right? So this is last recommendation that I would give is develop unified green hydrogen standard protocols, accelerate test lab infrastructure, adopt global standards, create single window approvals, and support industry capacity building through various efforts, right? I think with this, I have come to the end of my presentation. It was, we are still left with about 5 minutes, and um, should there be any questions or any submissions, I would be more than happy to answer them. And just a small request, if you're asking a questions, kindly switch on your camera so that I can have a view look at you. So over to you, Dr. Lakshman. I have finished with the presentations and uh, would be happy to get the honest feedbacks from all of you.
Yes, sir. It was a very nice and technically strong presentation from your side because we are not getting any information related to standardization and regulations of the green hydrogen. Okay, we have seen most of the literatures also. We find the data literacy in that. But today's presentation is really informative for us. You have provided the number of problem statements also for the research scholars. Then you have provided the future research directions also for doing any kind of the research. Then the most important thing that what you have discussed related to the hydrogen, as we can make the blend of the hydrogen with any other substance, what will be the imbrittleness in the piping. That is another research area that you have disclosed. That is very nice one. So overall, 100 out of 100 marks I will give you because I like your session, which is very, very important, sir. Yes, any questions from the participants?
Thank you so much.
Any questions from participants? Sir, these standards and regulations are only for the green hydrogen, or we can use these standards and regulations for gray hydrogen or any kind of the hydrogen also, or we can say the pink hydrogen also.
So I mean, these are primarily for green hydrogen, as I look at it. Some of them, yes, may be applicable even to gray hydrogen because when we talk about gray hydrogen or pink hydrogen, they are little inferior because green hydrogen is something which is the purest form with least carbon emissions, yes. And therefore the standards and requirements are quite stringent.
Yeah. And sir, you have discussed about the we required the purification of the hydrogen, that is 99.999%. It may require. How we can purify that hydrogen, because once it mixes with the any other gases, there may be the chances of liquefaction of the remaining gases. So how we can check that?
So nice question, Dr. Lakshman. See, what I'm talking about is 99.999 is at the output of your electrolyzer. Right. Once you're bottling up green hydrogen, I'm talking about that purity level, right? Anything below that, and you said, right, if you're blending it with any other glass, still it is requiring 99.99. Because if you have, traces of any moisture or traces of any sulfides, etc., seeping into the blend, it will lead to mass corrosion of all your equipments, right? If you use wrongly blended hydrogen in your automotives, right, it's going to be catastrophic. It's going to, completely destroy your device.
Yes, I think Mohit wants to speak. Yes, Dr. Mohit. Yes, any question? Mohit? He has raised his hand, but he is not able
Sir,
to answer.
Good evening,
Am I
sir.
audible, sir? I want to ask
Yes, sir.
one question. This is regarding the safety, sir. If suppose we want to have a lab in suppose institute, so while putting the hydrogen cylinders, what care we should take, like whether it is, there are some electricity lines are going around, and maybe when we put those cylinders, is it allowed if there is a high temperature, like sun rays are directly coming on that cylinder and all. So these safety concerns, I would like to know, sir.
Yeah. Dr. Mohit, nice question.
Sir, please. Sorry to interrupt. He is Dr. UV Avsarmol. He is the HOD of our department of AIT
Okay.
Mechanical. Yes, sir.
Okay, sir.
Okay. So, a very nice question, I would say. And yes, there are standards which you need to adhere to, because you cannot falter on those things. Everything is very well defined when we look at the safety standards. Uh, Even the placement and the external temperature which has to exist. The proximity of any power transmission lines, etc. Those are all defined on the standards, and they are very well documented. And if you need, we can discuss it offline, and we can share those data.
Thank you so much, sir. Thank you so much.
Yes, any other
Thank you so much.
question?
Good evening, sir. I am Dr. Jnanamurthy, Anna University, Tamil Nadu. My question is, for example, you are follow the every country's different standard. How will be the collaborate the single standard, or it is possible in future? It will be like that only, sir.
So, Dr. Ganamurthy, in this, I would say, when we look at the standards, qualifying standards for anything, right?
Yes.
There are minimum standards which have to be adhered to, minimum common standards which need to be adhered to, and then this is on the lower extremity, and on the higher extremity is you are adhering to most of the standards, right? If my electrolyzer, let's say, if India comes up with the BIS comes up with the standard wherein the electrolyzer it says ki it should be able to work in the temperatures of -20 to, let us say, +50 degrees centigrade, right? Whereas Germany, let's say, it defines a standard of working in between -10 to +25. So if I am, as it is, making the devices which work from -20 to +50, it automatically qualifies the one which are required in the foreign country. So my standards in case of India are going to be little more stringent and more accommodating when we compare it with European standards, because there, as I said, the plateau temperature is about 25 degree, and may not be applicable to India. So that is where the standards are, and if that is acceptable, and I'm sure those standards, I have not seen any higher standard being rejected by a country which itself is adhering to certain lower standards. I hope I have
Okay,
answered
sir.
the question.
Thank you. Yes, sir. Yes, sir. Yes, sir. Sure. Thank you, sir. Thank you, Lord.
Okay, sir. Thank you very much for your nice session and your time with us, sir. We are very glad to meet you, sir, and we'll look for the collaboration also.
Thank you so much.
Yes, sir. Yes, sir. Thanks a lot,
I've
sir.
shared my details. I've shared my details in my presentation on the
Yes,
last
sir.
slide.
Yeah.
And I hope that is being seen by everyone. If someone wants to get in touch with me, they can certainly get in touch with me. No issues.
Okay.
Hello, Dr. Sir.
Yes, sir.
Hello. I am having one doubt.
Yes, sir. Yes, sir.
Uh, Hello, good evening, sir.
Good evening.
Just I am having one issue. Many of times we have heard that ISO for safety, that is 9,000, and 9,000 is for quality and 14,000 for safety. Like that, hydrogen is nothing but the evaluation nowadays. There any kind of the ISO standard have been formed. If it is acknowledged, then kindly share with us.
So, I mean, there are standards, Dr. Sushil, and I mean, we can definitely discuss this offline because I'm sure it's already 7:31, and the next speaker, Dr. Lakshman, I think would be there. Dr. Sushil, you can get in touch with me separately, and we can discuss this.
Yeah, yeah, yes.
Yeah. Okay, okay, sir. Thank you, sir.
Okay, thank you. Thanks a lot.
Yes, sir. Yes, sir. Good, sir. Welcome, sir. Hello.
Good evening.
Hi, good evening, sir. Good evening. Welcome, sir.
Okay. Okay.
Yeah,
Thank you for,
yeah.
first of all, thank you for inviting me.
Yeah, yeah.
So, so I'm just starting sharing my presentation.
Let me introduce, sir. Within 2 minutes, I will introduce you. Okay, good evening, sir. Dr. Narendranath Ghosh is a professor at Birla Institute of Technology and Science, Birla Goa campus. He is the fellow of Royal Society of Chemistry and visiting professor at University of Leeds, UK. Currently, he is one of the editor in the Journal of Material Science published by Springer Nature. He obtained his MSc in 1994 and PhD in 1999 from the Indian Institute of Technology, Kharagpur. He pursued his postdoctoral research in the University of Delaware, USA. His broad area of research is nanoscience, nanotechnology, particularly the synthesis of nanoparticle, nanocomposites, and their applications. From 2020 to this year, Professor Ghosh has been placed among the top 2% most cited scientists in the world for both the categories like career, long database, and single recent year dataset. So I welcome you, sir, for your session. Now you are free to share your screen.
Thank you, Professor Lakshminarayan.
Yes.
And again, thanks for inviting me. I hope that my talk will be useful for those who are attending. And from the beginning, I'm telling you that apart from this talk, in this talk, I will try to give just some idea of what kind of research also we are doing. Basically, I am a material science, though I'm working in the chemistry department. So if anybody wants to collaborate with me, they are more than welcome.
Yeah,
Okay.
yes. Yeah.
So I am starting enter.
Yes, sir. It is visible, sir. Just press
Okay, it is
F5.
okay.
F5.
F5.
Yeah. Yes, sir.
So the again, good evening, everybody. And in today's talk, I will try to discuss about some nanostructured materials, how we can use it for as a catalyst. It could be electrocatalyst, it could be photocatalyst, or it could be photoelectrocatalyst for the hydrogen evaluation reaction. Now there are 17, all of us they know that there are several sustainable development goals which was adopted by United Nations for the betterment of the society, our living standard, our requirements, the requirement of this modern life and technology, improvement of the environment, which is essential very much. So for this reason, one of them is the SDG 7, which ensures the availability of modern energy for all by 2030. All of us we know that now the fossil fuel is depleting. We have used it for the so many decades, and now it is reducing because the source is limited. And not only that, it is as the carbon dioxide and gas is emitting, it is also not good for the environment. And we see that several issues associated with that. In that case, that another new, in that case, I wouldn't say new, I would say that people are knowing it, but now we are enforcing it, that lots of research on hydrogen as alternative fuel. Hydrogen is alternative fuel. There are a couple of reasons behind it. First of all, it's high energy density. It is its energy is much more than around two to three times than conventional like kerosene or gasoline. It is clean. If when it is if you burn it, no carbon dioxide or any gas will emit. So it is very easy to say that we are having a huge amount of water in the sea, and so generation of hydrogen or hydrogen technology is, though it is very interesting, but we have to overcome couple of limitations. One of the limitation what people are working on, one sector is that how we can generate it easily, cost effective way. And we must have to know take care of one thing, that to produce hydrogen from water splitting, we should not produce any other gases, or you have to use some other energy which can cause problem to the environment. Apart from that, transportation of hydrogen gas is an issue. Consider that if we are, when we are driving a car, and with our car, instead of having a petrol tank, we are having a hydrogen cylinder. It is very risky, isn't it? So that hydrogen safety, how we can very safely use the hydrogen, it's also an emerging area of research. However, in this talk, I will discuss about how we can produce hydrogen through water splitting. Because when we are talking about hydrogen economy and all this, we must have an overview that what are the different aspects of generating hydrogen and to use it as a fuel. So there are two popular ways. One is the photocatalysis, another is the electrocatalysis. Obviously, now when we are the first part of my talk, I would talk about the photocatalysis, and then I will move it to the electrocatalysis. So couple of things are required when we are talking about the photocatalysis. Obviously, we will see that you will try to find out or develop the catalysis which is active under the sunlight radiation. And I will talk about that. Obviously, when we are talking about the sunlight radiation or visible light radiation, we are talking about the semiconductor and how we can achieve it efficiently. For that, we have to take care of the catalysts band gap energy, the band structure, optoelectronic property, how we can overcome the activation energy. Similarly, when we are talking about the electrocatalysis, we have to find out how many active sites are there, how stable they are, and also that how conductive they are. Because here in the electrocatalysis, the charge transfer is a very important issue. So keeping all these issues in mind, several researchers from every corner of the world, we are working on developing the catalyst for water splitting. Here I am showing you a very old picture where that Dr. William and Anthony, they are demonstrating the the water electrolysis in a small tube, and there is a platinum wire there, and they are attached it with a voltaic plug, and there is a discharge at the tip of the wire. They are gradually see that the hydrogen and oxygen are evolving. This is that means that it is the water electrolysis producing hydrogen, oxygen. It's a grand old reaction as the research area. But this I have copied it from a paper published, is a review paper which is published in the Review on Molecular Chemistry and Engineering, where the author has shown that how the exponentially that huge amount of number of papers publishing in this area are increasing with the year after year. It's okay. So with this number of papers reflects that how much huge amount of academic research is going on, which is very, very essential. We must not, I want to emphasize one thing, we must not ignore the academic research, because it establishes the science behind of any technology. Now I'm coming about the water splitting reaction. Obviously, as I told you, my first part of the talk is the water splitting by solar light driven, and when we are talking about the water splitting by solar light, obviously it is coming in our mind that photovoltaic assisted electrocatalysis. So here we have to develop the photocatalysts, and also that there is one more technique to generate the for the water splitting is the electrocatalysis, and now we are combining the photocatalysis and electrocatalysis, which is known as electrocatalysis or electrochemical cells. However, the one very important part is the price of the hydrogen, and that target is make it around $2 to $4 per kg. That is the target is set by the United States Department of Energy, and this water splitting has reported by Professor Fujiyama and Honda back in 1972, which attracted the attention of the scientist. So this is the example how the water can split, and obviously during the water splitting reaction, we know that hydrogen evolution reaction, that 2H plus 2E plus H2 is a 2-electron system where the production of oxygen by water splitting, it's a 4-electron transport system. This thing is important because when we split the water, OER, that means oxygen evaluation reaction, and hydrogen evaluation reaction occurred simultaneously. Now, as the OER, oxygen evaluation reaction, is a 4-electron system, it is little sluggish. So, people are working on developing very efficient OER catalyst also. Now, when this water splitting is happening, obviously it will follow our very famous Nernst equation, A is equal to E naught minus RT/NF by ln key. So here you know the potential, you know that E naught. So when we are talking about the potential, obviously we take a reference, and E is equal to E naught is equal to 0.0591 divided by n log activity of H plus, which is the, we can say it is the pH. So obviously it is coming E is equal to E naught minus 0.059 into pH. Hence, we can see that the value E we can change by changing the pH. Okay, it will vary. So we can, I mean, in the few slides, after few slides, I can show you that how pH is changing. Now, it is a, people have calculated the Gibbs free energy for water splitting is equal to 237.2, where the standard del E naught is equal to 1.23 volt per electron transfer. This number is very important when we will discuss about the electrocatalysis. Now, when we know that the minimum energy required 1.23 volt, so we have to irradiate it such a wavelength which is around 1000 nanometer or shorter. Though I am talking about the HE, the hydrogen evaluation is still on the laboratory scale, but there are several installations are happening which is in the range of the commercial. Here there is one of the diagram which I have seen is published in the Nature in 2021. Here you can see that there is a plate which is coated with photocatalyst, and there is a flow of water, and they are slanting because how it should be shined by the sunlight. And then what are the gases? There is outlet. What are the gases coming out? That they are collecting it. That is another flat panel, and it is the this was published in energy technology in 2015. So there they are giving a block diagram, a schematic diagram how this HER or hydrogen can be commercialized and can be make a hydrogen production panel reactor. So I am not going in details, but I am showing this as that people are working on that. Now I am coming the photocatalysis. See, when obviously all of us know that when we are having when we perform a reaction, the reaction happens going forward when they cross the transition state or they have to go through the activation energy. Hence, this here you can see that in the pink line and the green line, they are representing the water splitting, but the green line is that it is presenting the without catalyst, uncatalyzed water splitting, where we can see the activation energy is 500 kilojoule per mole, whereas when we use the catalyst, that energy is decreasing significantly. Therefore, our main goal would be that how efficient we should create or we should make catalyst which can reduce the activation energy significantly. We have to, because for that this energy needs to be crossed. So photocatalysis, we all know that for photocatalysis we need a semiconductor. When it is irradiated by the light, it could be UV, it could be sunlight, it could be any light of your selections, but it depends that the nature of the semiconductor, that when it shines, the electrons from the valence band, it leaves couple of holes and it accumulates in the conduction band. And the energy difference between the valence band and the conduction band, we call it the band gap. That means to jump the electron from valence band to conduction band, minimum the energy required is the band gap energy. Here in the picture I am showing you that the reaction when we have shown this picture, here you can see that here for 2H plus twice E is equal to H2, and here 2H2O plus 4H plus is equal to 4H plus O2 plus 4E minus. One is oxidation, another is reduction. Okay, so when it is the reduction, here it is 4H plus, it becomes to 2H2. That means the electron, it requires the involvement addition of the electron, and it happens and the conduction band, because there the density of electron is more, whereas in the valence band the water, it splits into 4H plus O2. So here the oxidation is happening. So the photocatalytic reactions, it goes through a couple of stages. First, light absorbs by the semiconductor, then formation of photogenerated electron and hole pairs, then migration of the photogenerated electrons on the conduction band, and depending upon the band gap energy, recombination can happen, which is not good for the photocatalysis. And then the necessary reactions, the redox reactions occur on the semiconductor surfaces. Like here you can see that on the conductance band there is reduction reaction is happening, and in the valence band the oxidation reaction is happening. Now there are a couple of questions. We know that now we understand that if you read it with a appropriate light, the semiconductor, it can generate the photogenerated H plus holes and the electrons. Now to make this jump, we need the minimum band gap energy. Now, if the band gap energy is too high, the visible light or solar light cannot cross this band gap energy. So you need a stronger, more wavelength, more frequency, more energetic radiation. UV could be one of them. So, but there is a problem, because for the large scale application, that UV generation, utilization of UV, not only the costly, but also it is the hazardous radiation. It is not good for our health. Therefore, we need to gather, we understand that we need the semiconductor which is lower energy. Fine. If in the case 3, in the case 2, if the band gap energy is too small, so any low energy radiation, if you can irradiate it, easily the electron can jump from valence band to conduction band. But as the band gap energy is too small, quickly those electrons come back and again join with the H plus. So this is called the recombination. That is also not good. So what we have to do, we have to find out a catalyst which is an appropriate band gap energy, so that if you can use the moderate energy, so that it can be radiated by visible light or sunlight, and also the recombination, if not no recombination, but the minimum amount of recombination happens. Here, this I'm showing in the diagram that first the E value of H plus plus H2, if you can see at page 7, that E0, if we take the NHE, normal hydrogen electrode, it is 0. So 0 minus 0.059 into 7. So for H here, the potential is minus 0.41, whereas for oxygen, it is the 0.82. That means we need to select a catalyst, photocatalyst, whose conduction band, the position of the conduction band and the position of the valence band falls within minus 0.41 and plus 0.82, just outside that. Or other way, that they cover these two values. Okay. Now here at the down, I am just showing you that when the titanium dioxide, a very well-known photocatalyst, when it is irradiated, its band gap energy around 3.2. When it irradiates, its valence band and conduction band is above the potential of HER and OER. However, as its that band gap energy is too high, you need to activate that. You need the energy, sometimes high energy, sometimes it is the UV. So this is the pictorial presentation of this band gap engineering. If, say, consider that we are standing on the surface of the earth, one person is jumping, reaching high, but the gravitational force, it pulls him down and quickly bring him on the surface again, which is exactly the same case for the semiconductor. You irradiate, electron goes from the valence band to conduction band. If they are close, the Coulombic force again brings back these electrons near to the valence bond. That means the recombination it will happen. Now, what we should do if we want to keep the person not above the surface of the earth. What we can do, we can put a stool on the surface. The person can jump and stands on that stool. So it is not coming back to the surface, but it is reaching a little above the surface. So same thing we can do, that if we can make a heterojunction by combining two types of semiconductor, obviously their band structure should be compatible. Then if we can irradiate it by light with appropriate energy, then the photogenerated electron and the holes, they can separate effectively. And as they are separate effectively, it was not possible for them to quickly recombination. If you look at this picture, here you see that semiconductor A. Here the band gap, there the valence band is little higher than the semiconductor in the B band gap position, whereas the CB of the semiconductor A is little higher than the semiconductor B. So when the radiation is happening, both of them, they will generate photogenerated charge carrier, and then the electrons which are in the semiconductor A, they migrate to the conduction band of the semiconductor B, because it's here for the semiconductor B, the energy level is relatively less. Similarly, the H plus will migrate from the semiconductor B, valence band of semiconductor B, to the valence band of the semiconductor A. Now you can see that the electrons are accumulating on the CB of semiconductor B, whereas the holes, they are accumulating on the valence band of semiconductor A. That means that separation is happening. So which prevents or minimizes the recombination process. Here I am showing that there are the band gap of different materials with different band gaps, and when pH is 0, the E value for H here is 0, because E is equal to E naught minus 0.059 pH. pH is equal to 0, E naught H plus is equal to 0, so it is 0. But in that case, for the OER, its value would be plus 1.23. Okay. Here you can see that several examples of like phosphorine, some tungsten, some graphitic carbon nitride, and then SnH2, some molybdenum sulfide, tungsten oxide. So their band positions, conduction band and valence band positions, they are covering the potentials of HER and OER. That means that if we can use and appropriately irradiate them by light, appropriate light, it will show the water splitting. In the again, this thing that if you look at the picture below, actually purposefully I gave this because here in the above picture pH is equal to 7, pH is equal to 0, whereas when pH is equal to 7, again if we put the equation is equal to E naught minus 0.059, then the E value for H here becomes minus 0.059. into 7. Just hold on. Which is around minus 0.413. And similarly, if you put this value to this, it will be here, it will be 1.23 minus 0. Minus just hold on. It will be 0.817. That means that the same reaction is happening, but with the change of pH, these their potentials are changing. So that's why whenever we present this kind of diagram, obviously we present two things. One is that which is the reference electrode. Here it is the NHE, and that here is the what is the pH. So this also shows that which photocatalyst will be active at what pH. So when we are talking about the heterojunctions, there are several positions can happen. If you look at the first ones, you can see that the position of CB and VBA is above than CB and VBA both of semiconductor B. That means their energy level is not at all matching there. We call it broken gap. Whereas if you look the next diagram, where the positions of VB and CV of semiconductor B is lower than the CB and VB of semiconductor A. We call it the straddling. And when you look at the third diagram, where the position of CB of A is higher than the CB of B, whereas the VB of A, position of VB of B is higher than the VB of B. It is called staggered. So these kind of combinations are important to create the heterojunction. So we have to know that what is the positions of CB and VB when we will create the heterojunctions for a particular photocatalysis reaction. What I mean to say is that water splitting is one of the photocatalysis reaction. Now, when it is the if you look at the picture below, that type 1 straddling type, we call it type 1. So here it is happening, both of them, they are radiated, then the charge separation is photogenetic charge separation is happening. Now, as the VB of semiconductor A is higher than that of the semiconductor B, the holes are migrated from VB of A to the VB of B. Similarly, electrons are moving from CB of A to CB of B. Well, then what we are seeing? We are seeing that because of this heterojunction, the band gap energy, the band gap is become smaller. That means that charge the probability of recombination has increased. So we cannot say that it's a type 1 is a very effective uh, a very effective charge separation. So since both electrons, holes and electrons are accumulate on the same semiconductor, and the electron hole pairs cannot be effectively separated by the type 1 heterojunction catalysis. Now I am coming to the staggered gap, which is the type 2. Here you can see that after photoradiation and the generation of photogenerated charge, the electrons of the semiconductor A, which are situated in the CB, that moves to the CB of the semiconductor B. That means the electrons are accumulating on the in the CB of semiconductor B, whereas the holes are migrated from the VB of semiconductor B and going to the VB of the semiconductor A. That means the difference, the electrons are accumulating on the CB of semiconductor B, and the holes are accumulating on the semiconductor A, the VB of semiconductor A. That means effective charge separation is happening. Some of the examples: if you take the titanium dioxide Gc3n4, titanium dioxide band gap energy 3.2, Gc3n4 around 2.27, around 2.7. Graphitic nitride oxide, tungsten oxide, bismuth ferrite, graphitic carbon nitride. These are all the examples of the type 2. So this type 2 was this is the paper which proposed this mechanism. Here this paper was published in 1995 in the Journal of Photochemistry and Photobiology. Now there is another thing, type 3. In type 3, you can see that the positions of CB and VB of semiconductor A and B, they are not at all matching. That's why the heterojunctions, you can see that when they are irradiated by light, movement of electrons and the holes cannot occur. We call it the broken gap heterojunction. So it is not a suitable heterojunction. Now, if you look at the type 2, here we can see that the electrons are going to the accumulating in the lower energy level on the CB, and the H plus, the holes, they are accumulating on the VB of lower energy level. That means that they are the electrons who are in the CB of semiconductor B, they are having relatively low potential, low energy, and similarly that for the VB, that the H plus are which are accumulating in the VB of A, they are also having little less. That means they are not very strong reducing or oxidizing agent. electrons are reducing agent, and Vb, the H plus holes are the oxidizing agent. Therefore, another type of heterojunction was created, which is known as PN heterojunction. Here, we play with when the heterojunction, the two semiconducting material, they contact with each other, and their Fermi level, they adjust their Fermi level and become the same. The Fermi level is the highest energy level of an electron can occupy at the absolute zero temperature. Okay. So they adjust. So it will, you can see that after adjustment, as the in the junction on the interface between the two semiconductors, in one case on the surface, on the interface, one layer of positive happens, and in another side, another side of the interface, the negative charge accumulates, and as the electric field generates, then from the p-type semiconductor, the electrons which are generated due to the irradiation, they move to the, due to this attraction, it moves to the CV of E minus, whereas the same case, in case of the p-type semiconductor, as they on the interface, their charges are the negatively charged, the H plus from Vb, they moves to the Vb of the p-type semiconductor. But also we understand that this charge separation, the formation of this charge layer, is only occur at the interface. At the bulk, it is neutral. So this is an example of cobalt ferrite, zinc ferrite heterojunction. When you see that before contact, you can see their Fermi level, and see before contact there was no charge separation or electric field generation happened. When they are coming in contact on the surface of the zinc ferrite, it becomes on the interface, towards the zinc ferrite, it is positively charged, and for the cobalt ferrite, it becomes negatively charged. And for that, and you can see that Fermi level, they are matching, they are become aligned, and electrons are moving from the lower CB, and the H plus are moving to the higher BB. Now we are talking about, and we will discuss about another type of heterojunction, which is known as the Z scheme heterojunction. Here, again there will be two semiconductor conducting material, and at their interface there will be an electron and a mediator, which will facilitate the movement of electrons which are generating in, say, PS2. That means that the semiconductor 2, who are having the lower energy of the CV, that can accumulate, that can move to the H plus, which are in the VB of PS1. And so this mediator, which is basically they are the acceptor donor pair, that's why called A by D. So the electron A is the acceptor. It accepts the electron, becomes D. D is the donor. They release the electron, which can react with the H plus. It is a very interesting mechanism which was pointed out in 1979, and it is the mimic of the natural photosynthesis process. In the photosynthesis process, you can see that this kind of thing is happening. Say your chlorophyll P680, when it is radiated by light, obviously here it has becoming excited. It becomes P680 star. Okay, and the electrons, after going so many redox reaction, it reaches to the P 700, which when it's irradiated by light again become excited to P 700. That means the electrons of PS2 is combining with the H plus of P 700, and the electrons of P 700 stars, they combine with the NADP star and make it NADP plus to NADP, whereas in the other end the water is degraded and produce the H plus and oxygen. That's why you can see that how the chlorophyll under light radiation, it can produce oxygen as well as it produce the oxidized form of NADPH. As it looks like Z, if you look that from P60 to P68 star, then another arrow, and then P70 to P70 star, it looks like Z. But here, all the mediators are liquid in nature. Hence, people are working on that to have an electron mediator if it is solid. That means the catalyst becomes a solid. There should not be any liquid part of it, which is easy to handle. So people are inserting any high conducting metal, particularly platinum, gold, in between the interface of the PS1 and PS2, and the mechanism remains the same. Here, instead of liquid, the electron mediator is the solid. The issue with that is that all the platinum, though it is very, very efficient, but it is highly costly and availability is limited. Hence, people are working on that we can, instead of platinum or gold, we can develop some other type of electron material which is cheaper. This mechanism, as here the PS1, two semiconductors, PS1, PS2, and the mediator, all are solid. That's why it is known as all solid state Z scheme heterojunction. So it is first proposed in 2006 by Dr. Tada in Nature Materials, and that is the scheme they're talking about, where it is the titanium dioxide, gold, and TiO2, the three component heterogeneity system. We have also made one heterojunction which is made of cobalt ferrite and a conducting and a porous carbon, which is has semiconductor nature, and we have placed the copper nanoparticle in the interface, and we have demonstrated that it can under sunlight or radiation, it can act as a all solid state jet scheme mechanism where metallic copper can act as an electron mediator. And using this, we have done some photodegradation reaction where to degrade some dyes and some antibiotics. Here, as the holes which are remaining in the higher VB, that the holes they are having higher potential energy, and the electrons which are accumulating on the higher the CV side, it is having more reducing ability. And if we can use as a H2O2 in the self-sacrificing agent, white water decompose it produces OH dot, and this OH dot can degrade the antibiotics. The mechanism and antibiotics we have already described in a paper, but right now I am not discussing about this. After this also, that people have developed a direct Z scheme mechanism where there is no mediator is there directly from here. This diagram, it shows the Z scheme of TiO2 and graphite carbon nitride. As I told you that graphite carbon nitride has the band gap of 2.7 and TiO2 is around 3.2 electron volt. Here you see that in absence of the mediator, still the photogenerated electrons of at the CB of TiO2, it moves to the H plus to the VB of, sorry, there is a little mistake. It should be the VBH plus. It should be of the graphite carbon nitride, and leaving that the H plus at the VB of TiO2 and the electrons at the CB of graphite carbon nitride. And then in the reduction is happening on the CB of graphite carbon nitride, and oxidation is happening at the VB of TiO2. So this is the mechanism what I was just described, and if you can see that at the here the potential the difference between the potential energy of the accumulated electrons at the CB of graphite carbon nitride and the VB of the holes at the VB of the TiO2, they are falling within the potential range of 0 to 1.23. So this catalyst has the potential to be used as the water splitting catalyst and but the pH has to be 0. So this was proposed in the PCCP by Dr. Yu in 2013. Now another scheme, it is known as the S scheme mechanism. Here also the combination of H plus and E minus happens. Here, instead of telling the semiconductors as semiconductor 1 or semiconductor 2, we are calling one type of semiconductor. It is that oxidative photocatalyst, OP, oxidation photocatalyst, and another one is the RP, which is the reduction photocatalyst. Here, for the same type, when OP and OR, they are having different Fermi level. When they come in contact, that they become the levels, adjust the level, and here you can see that there is a band structure, bending is happening, and because of that, at the interface, that a double layer is forming, electrical double layer is forming. In the RP side, it is the positive one. In the OP side, it is the negative one. So this is happening after contact, but as of now, the catalyst we have not irradiated by light. When it is irradiated by light, the VB of OP that it generates electron, it goes to the CB of OP. Similarly, at the VB of the RP H plus produce, and in the CB it goes to the accumulates the E minus, and then because of this negative charge and the positive charge, as the VB, they come in the negatively charged side and the electrons come in the positive and they combines. Hence, the VB of the OP, it is accumulates the H plus, the strong H plus with the strong oxidizing ability that remains, and on the CB, the electrons at the higher reduction potential that stays. So here we are calling it OP because that here the oxidation happens at the VB, and we are calling it RP because reduction is happening at the CB. So it was proposed in the applied colleges B in 2019. So this is one of the scheme catalyst we have made, heterojunction we have made. Here we have conducted the, we have made one is the graphite carbonate and is the cobalt ferrite, and they have combined, and this catalyst what we have used for the degradation of various type of dyes, which happens mainly on the CB of the graphite carbon nitride. Apart from that, there are several other types of catalyst also there. One is called Schottky junction, where the semiconductor and it is attached with metal, and when this heterojunction is irradiated by the light, the electrons, which are photogenic electrons, which are residing at the CB of the Gc3n4, it migrates to the metal. That's why it is called the Schottky electron, and there in the metal surface the reduction happens, and as usual with the VB of the graphite carbon nitride, oxidation happens. Another thing is that which is called surface SPR. As we know that SPR is mainly or prominently shown by the gold, silver. You can see that with the change of particle size of the gold particle or the silver particle, nanoparticle, their colors changes. So here when a Gc3n4 is attached with the just say gold nanoparticle, when they are irradiated by visible light, as I have told you that they are with different color, which can be detected by our naked eyes. That means that the SPR phenomena is happening within in the visible light irradiation. So the electron which are generated in the metal, it moves to the CB, and there the redox in the CB of the graphite carbon nitride, that means in the semiconductor the reduction happens, and the VB the oxidation happens. And in case of graphene or carbon nanotube, as we know that they are highly conducting, the electrons, the photogenerated electrons, they migrate to the either graphene or carbon nanotube and quickly transferred to some other place so that it cannot recombine, and on the surface of the graphene or carbon nanotube the reduction happens, and in the VB of the graphitic carbon nitride the oxidation happens. So I have already discussed this. Now I'll quickly go through the electrocatalysis. So here you have to apply some potential. Here in the electrolysis there is no no business of radiation. Here we apply the potential, and here you can see that in the anode oxygen generates, in the cathode hydrogen generates, in the so in the HER it can happen in the acidic medium, it can happen in the alkaline medium. I have given the reactions what is happening in the HER, in the alkaline medium, and what has happened in the acidic medium. Similar things also simultaneously OER happens. So when we are talking about the HER, I would like to give you a very brief description of what is the mechanism. Basically, there are three important steps are there. So, but the mechanism of the acidic and the alkaline media, they are little different. So the main three steps are Volmar step, Tafel step, and Eros-Bisky step. The alkaline medium also it is the same. So in acidic medium, the solid black color bar, you can consider it is the surface of the catalyst where H plus first come, and also the electron comes. They combine on the surface, forms OH dot. Then as it is acidic medium, on that OH star, another H on the surface, another H plus sits, and electron comes. So on the surface there are two H star, they resides, and then when they combine it produces the H2, which is the Tafel slope. Otherwise there could be another mechanism can possible where the H where on the catalyst surface first H plus comes with electron, it becomes H star, and then on that directly H plus attacks, and by that the H2 it generates. So these three steps are very important. But on the contrary, when it is the alkaline medium, the water molecule first comes and anchor on the surface of the catalyst. Electron comes there, it release the OH minus, and one H star on the sits on the surface of the catalyst, and then it is attacked by the water, and again OH minus it releases, and there you can see that two H star are anchoring on the surface. They combine as usual. That is the Tafel slope, the Tafel step. H2 releases. On the contrary, another mechanism, it is the H star is already sitting on the surface. Electron is coming. Water is directly attaching that H radical or H star, which is the and then it releases OH minus, as well as it releases H2, and then again make the catalyst surface available so that water can anchor on them, and also the electron can attach with that. So we can see that there are two mechanisms are different. And when we study the kinetics, we take the taper slope where the H2 is generating. We take it as a very important step. All the steps are important, but we determine one slope which is known as the taper slope. So here with this mechanism, we can see that the absorption of ester is very, very important aspect for the catalytic reaction. So obviously, hello?
Yes, sir.
Hello?
Hello, sir. Sorry to interrupt you.
Mhm.
Sir, we have some time limitations, so we have to take question answer session also because the meeting
So,
scheduled for 9 p.m. only.
okay, so I'm just quickly finishing it.
Yes,
So
yes,
that
please. Yes,
so
please.
the Gibbs free energy that which is del H, it is very important for that. And ideally, we take it that del H, when the del H is very close to zero, that catalyst is very, very effective. Here is the this type of plot is the known as the volcano plot, where you can see that platinum is almost on the tip of that volcano plot. That's why we consider its value. You can see that it is near zero, the del G value. We consider it's a very effective catalyst, and it is an effective catalyst. But you know that as its cost is involved, so people are working on replacing platinum by some other material. So material scientists are working to making different composites, and we are all working on that. And so here, that is the diagram. You can see that red one is with catalyst, and the black one is without catalyst, how it looks. And so though we are talking about that 1.23 is the energy, but in the real life situation, it is not like that. So the catalyst, they need some extra energy, which we call it over potential. So but our always attempt is that lowering the over potential. You can see that the red one is the in the right hand side, the red one is the ideal catalyst, where the over potential is very, very less. And when the actual catalyst, they are in the black color or the blue color, there is little high. So we have made different types of photocatalyst, which is like I have told you that, which is different types of cadmium sulfide, snowflake like, and the graphitic nitride. We made it the PN junction. We have done exfoliated graphitic nitride, cadmium sulfide, and amexine. Here the amexine we used as the electron mediator for the solid state. We have made another scheme, graphitic carbonate, bismuth ferrite, graphitic carbon nitride, cobalt ferrite, scheme, exfoliated graphitic nitride and cadmium sulfide, which is also a scheme, copper, cobalt ferrite, and porous carbon, Z scheme, like that. And also we are making some electrocatalysts like zinc, cobalt oxide, tungsten oxide for producing HEA. We are use the nickel cobalt sulfide and a combination of the TUS. We make the porous carbon from TUS and make it as a support to this nickel cobalt sulfide nanotubes, and which can act as a very effective catalyst. Again, we have made the graphitic carbonate, amexine, cadmium sulfide. So now I must say that for the last a couple of years, the amexine is becoming very prominent material, very hot material, and now the ambeans are also coming, which are also getting lots of attention. They can hugely use for the photocatalyst. So here I'm almost finishing my lecture. Here I just say that in our lab we have made different types of nanomaterials which we have used as electrocatalysis. We have used the photocatalysis. You can see that we have used a prototype which is solar light driven photocatalytic device, where really there you can see a water bottle which is a little dark color, dirty color water is there, and after the reaction it becomes the colorless, very transparent. It is the real wastewater sample from a dye industry, textile industry. So the water which is coming, I can say that it is reusable, but not for drinking purpose, because we have proved that when that the dye degrades, that is not mineralizing fully with water and carbon dioxide or nitrogen, not like that. Some small organic molecules are there. We have also made the different types of composites for the supercapacitor application. You can see that we have illuminated the lights, so the bits, as these are the layered structure of the amexines and molybdenum borides, which is known as ambeans. Right now, I mean, they are the layered structures. We have also made the exfoliated boron nitride. I'm just skipping this. So I'm thankful to my collaborators, to my funding agencies, and I thank you for your kind attention, and we can proceed to the question answers. And you can have my contact number here.
Yes, sir. Thank you very much for your session. It's purely scientific session that I have ever seen.
Yes.
Is there any questions from participant? Yes, any question from participant? I think, sir, there is no single question.
Okay.
Yeah.
So
Thank you very much for your session, sir. Your time and
thanks
your
a lot.
session. Yeah. Yes, sir.
Thanks a lot. Thanks for inviting me, and I'm very much excited to have this kind of session.
Yes, sir.
And I would be happy that to do any collaboration with anybody. And also, if you give me a chance in future, also I will appear and give this kind of lecture.
Yeah. Yes, sir. Thanks a lot, sir. Yeah.
Okay. Thank you.
Yeah. Here I declare that today's session is over. Thank you very much for your kind patience and attendance. Thank you very much.